Hey, this is Laura from the NEEC IBW Electrical Training Center, and in this lesson we're going to be looking at vector relationships in series and parallel RLC circuits. Okay, so here's our two circuits. Got a series RLC and a parallel RLC circuit. We're going to start with the series circuit. And first we'll look at what adds in series. So this follows the same rules as DC theory, and we should know that power adds, voltage adds, and resistance adds. And in this case I'm going to denote resistance with Z for total ohms. Now, what makes these circuits more difficult is when these components add, they don't add directly because each one is a vector that points in a different direction. So we're going to be looking at these vector relationships for our series circuit. And think of the mnemonic PEZ. Those are the components that add in series. Our vectors point in different directions because there's a change in phase between voltage and current dependent on whether we're looking at a resistor, inductor, or capacitor. So I'm going to draw the voltage vectors for this circuit, and we will have EL pointing up, ER pointing to the right, and that leaves us with EC for the capacitor pointing down. Now, because I want to demonstrate this relationship between voltage and current for each of these components, I'm going to add current to this vector diagram. And in our series circuit, we have this current coming around in the circuit, and it's the same everywhere because it is a series circuit. So my current here at R equals the current at L equals the current at C, which equals my total current. So in order to add it to the voltage vectors, I need to know which way it's pointing. And here's how we figure that out. The key is our resistor, because hopefully by now you know that voltage and current across a resistor are always in phase with one another. So when two vectors are in phase with one another, what that means is they point in the same direction. And so if I change to my actual pointer, there I can draw it in, and here is my current vector, which is the current for everywhere in that circuit, since it's the same everywhere. Okay, so we have all of our vector relationships here, and you might wonder, how does this relate to Eli the Iceman? Okay, so for our inductor, we know that that's the Eli portion, so I'm going to write Eli right here. Okay, and Eli means that voltage, E, is leading current, comes before current, I, and the L represents for the inductor. Now you have to imagine that these vectors, even though I show them fixed in place, are really spinning in a 360-degree circle, and their direction of rotation is counterclockwise. That's because we have 0 degrees here, 90 degrees here, 180 here, and 270 here. And that's the way things go in a circle, all the way around. So as these vectors spin counterclockwise, you see that EL is ahead of I. Voltage leads current by 90 degrees. We've got a 90-degree angle right there. Okay, now let's look at our capacitor. So that's Iceman. Okay, we've got I for current, leading voltage for a capacitor. And if we look how that works in with our vector relationships here, again, our vectors are spinning around here, And we see that this current is leading that voltage by 90 degrees. So this is why our L vector must be the up one and the C vector must be the down one, because Eli the Iceman, kind of like Ohm's law, has to work. Now let's look at our parallel circuit. So in parallel, think back, what adds? Power still adds in parallel, and current adds. So these are our pi vectors. So I will be drawing the current vectors for this circuit. This time I'm going to have IC pointing up. We're going to have IR as always, any R vectors at 0 degrees, and that makes my IL pointing down. And again, we want to compare current and voltage to see that relationship between one another. And we know that the voltage, my source voltage, is going to be the voltage across every component here in this circuit. So we'll do like we did with the series circuit, and in order to figure out the direction of our voltage vector, and by looking at our resistor, because we know that voltage and current for the resistor must be in phase. So I will go ahead and add our voltage vector. Now we're going to look at Eli the Iceman again. So hopefully you will see why IC is pointing up this time and our L component is pointing down. So let me write our Eli, which will be down here now because we're looking at the relationship between voltage and current for our inductor, our L component, and our circuit is spinning counterclockwise, or our vectors are spinning counterclockwise, and we have that 90-degree angle there, and indeed voltage is leading current by 90 degrees. So this vector relationship shows the Eli component for an inductor. On the other hand, if we look at our capacitor, write down our Iceman here. Okay, so looking at ICE, we know that current should be leading voltage, and indeed we see the current vector here for our capacitor is leading the voltage by 90 degrees. So our Iceman works. Okay, so hopefully that explains why sometimes L vector is pointing up, sometimes the C vector is pointing up. If you can't seem to remember this, a wise apprentice once taught me a mnemonic, and I'm going to write it down here, and it helps with the current vectors. So I'm going to write here, IC is up. Okay, and I'm going to leave the rest to you. Just say each one of these letters as an individual. And hopefully that helps you remember. Thank you. Bye-bye.
Made with Doodlecast Pro.